knowing the increasing and decreasing behavior for a function can help you get information about its rate of change, or, for example, if it's a function involving volume, knowing when it's increasing versus decreasing lets you know when the volume of, let's say, some fluid in a large tank is going up or when it's going down. Maybe it's a function involving hydrostatic pressure on a dam, and when that function is decreasing, you're at a shallow depth on the dam. When that function is increasing, you're at a pretty deep depth on the dam. So knowing the increasing and decreasing behaviors of function is pretty important. Now, when you have a graph of the function, determining the increasing and decreasing behavior is relatively straightforward. To determine the intervals where a function is increasing and decreasing, what you're going to want to do is come up with a systematic way of determining, okay, when is this graph going up and when is it going down, essentially. So here's your frame of reference when you're looking at increasing and decreasing behavior. You're always going to need to get the intervals from the x-axis. You're going to list intervals from the x-axis that let you know when the graph is going up and when it's going down. Well, see, here's the thing. When you look at a graph like this, you're probably kind of tempted to impose some sort of rule of gravity on it. For example, if you were to place a ball right here at this point of the graph, intuition, and I guess just basic physics, leads you to believe the ball would go down this way. And that's true. If this is modeling some sort of mountain shape, yeah, a ball would go down this way. However, you can't do that whenever you're listing increasing and decreasing behavior. You have only one frame of reference when you're reading a graph. You always have to go from left to right in the domain. So you're going to read the graph this way. So as you're reading the graph this way in the x-axis direction, you have to look at the corresponding y-axis or y-direction behavior to detail the correct increasing and decreasing behavior. So as this function, as the x values increase from left to right, this first portion of the graph, as x moves this way, the y values are moving this way. So on this portion of the graph will be said to be increasing until it reaches that peak point. So that's an example of increasing behavior. INC, abbreviation for increasing. As soon as you reach that maximum point, you're still going left to right in the x-axis direction. So that means the y values that pair with those x's are now going downhill from left to right. So there is a decreasing portion of the graph on that interval. And then as x continues to increase here, the graph goes back uphill for a little bit, so there's another increasing interval. And then once you pass this peak point, the x values keep on going to the right, you're now in a decreasing portion of the graph. So the frame of reference is to always read a graph from left to right when you're detailing increasing and decreasing interval behavior. So now, the intervals that I keep mentioning do come from the x-axis, okay? So I'll keep this graph here handy as we detail our answers. You're asked to determine the intervals where the function, the one we just graphed, is increasing and where it's decreasing. Refer to the graph on the previous page. So increasing and decreasing intervals always come from the x-axis. That's why you need to know those relative max and min turning points in order to get the correct behavior intervals. So f of x, the function is increasing on, so here's what you have to do. It's increasing on this portion of the graph, but you need an x-axis interval that gives you that behavior. So what that means is this function's increasing, well, essentially from minus infinity in the x-axis direction up until the graph reaches this point right here. So the most important value for detailing the interval from this point is the x value. The increasing behavior stops at x equals -2 when you reach that first relative maximum. So that means our first increasing interval is the x-axis interval from minus infinity to -2. Now, I'm always in the habit of putting parentheses on the endpoints, the numerical endpoints, of these increasing, decreasing intervals, because if I put a bracket there, that technically suggests I'm still increasing at the value x equals -2. Technically, since this is a maximum, you're neither increasing nor decreasing at that point. So that's why I've always had the habit of listing these with parentheses on the intervals for the interval notation I need for this kind of problem. Then, beginning at x equals -2, the function starts to decrease until it reaches the x value here. Now, the 9 is the y-axis value, but remember, since that's a y-intercept, that occurs at x equals 0. So that means the first decreasing interval you'll list is the interval from -2 on the x-axis to 0 on the x-axis, because that's the interval where that decreasing behavior occurs. It's always the x-axis intervals that drive the behavior, so what you actually need to list. So then the next interval, you start to increase past this minimum until you reach that maximum again. So again, the x-axis interval that drives this increasing behavior is the interval from 0 to 2. So that actually gives us another interval to list, 0, 2. And you're going to see me use this union symbol here because I'm having to actually connect two intervals that are separated. See, those are disjoint intervals, -infinity to -2 and 0 to 2. But since they are part of the same solution set for increasing behavior, I put this union symbol in between them, which is basically just looks like a letter U. It's just a set notation symbol that's used to glue two intervals together. Same idea with decreasing. I'm going to need to union this first decreasing interval with this last one. This last decreasing interval begins at x equals 2, and there's no other change in behavior. It continues decreasing beginning at x equals 2 going on to infinity, and that decreasing behavior never changes. So that means our final decreasing interval is going to be from 2 to infinity. So whenever you're prompted for increasing and decreasing behavior, remember it's always the x-axis intervals that actually drive that behavior are the ones that you need to actually detail. Okay? So continuing with our endeavors of graph analysis, I want to go over some examples of determining information from the graph of a function. So sometimes the graph is given. You don't have to make the graph yourself. Sometimes you just need to be able to get the information from the graph, which is a very vital pre-calculus skill. Domain and range are pretty important. You'll almost always be prompted for the domain and range by looking at a graph. So let me go back over the domain. Remember, the domain represents the set of all x values used to produce your 2D graph. Range represents the set of all the y values that are used to make this two-dimensional graph. And some interesting things about this graph, you've got a graph that starts here with an open circle. So going back to inequalities that we did earlier, anytime you see an open circle used in 1 dimensions or 2 dimensions, that represents a point that's not really there. I mean, that's kind of a starting point for the graph, and the hole is located at x equals -5, y equals 3, but it's intended to be a void point. But then it begins with a connected continuous graph, goes down a little bit, goes up a little bit. So see, there's increasing, decreasing behavior. Decreases, then increases, then it decreases, and that arrow indicates the fact that it continues decreasing, and widening. So it continues going downward and rightward past what you see here. So everything you need to know about the graph is right here on this page, or on this little snippet of the graph, to be able to answer these questions. So the domain is the set of all x values used to make the graph. Go back to that smashing analogy I did. If you take this entire graph, smash it to the x-axis, okay? What that means is this open circle here will get smashed down to that point on the x-axis, and it'll still be an open circle, okay? All this part will smash here, this part will smash to this part of the x-axis, and this part that goes on down and rightward will smash onto infinity. So the interval that represents the set of all x values on this graph is graphed right there, the little smashed interval that I've got plotted. It starts here at x equals -5, but notice the important thing about that open circle is technically that's not included with the domain. So your domain does begin at -5, but it's got parentheses around it because of that that open circle that's on the graph there. So the x value that begins the graph is -5 and it's void, and then continues on to infinity. And that is the proper domain of this particular function's graph. Okay? Range, similar idea. You want to take the entire graph, smash it to the y-axis, and then make note of any maxes and mins, because that's going to affect your range as well. So if this graph were smashed to the y-axis, this portion here that's indicating downward, all this would get smashed from -infinity and stick to the y-axis. All this stuff here would smash to this part of the y-axis. All the stuff here that overlaps would still smash to the same region on the y-axis, but I wouldn't be able to go any further past this maximum right here. So the last place that would get smashed to is right there at y equals 6. So, and even though there's not an actual dot there, I would go ahead and assume, and you can take the liberty of assuming it as well, assume that the actual y value attained at that point is 6. So that means the range of this function, remember, read the y-axis from least to greatest for its intervals in interval notation. The interval for the range would be from -infinity on the y-axis up to and including the value 6. So since the 6 is intended to be an actual point on the graph, I will go ahead and include it with the interval notation I need there. Okay. The intercepts, those are pretty straightforward. X-intercept here looks like it's at -2, 0. And there's another x-intercept over here, 1, 2, 3, 4, 5, 6, 0. And again, those are the x-intercepts. The y-intercepts, correction, y-intercept, singular. You can only have one for a function. Looks like it occurs right here at the y value 1, 2, 3, 4. So your y-intercept is at the point 0, 4. So notice the different things you're asked for use similar notation. Interval notation uses parentheses just like coordinate point notation. So within the context of the problem, you got to make sure you know what your symbols stand for and what they're used for. These are coordinates representing x and y intercepts on a graph. These are intervals representing domain and range from a graph. Okay. Now what this is asking you for, this is asking you for f of 5. This is the graph of the function f. We don't have a formula for it, and earlier we evaluated this by plugging the value 5 into a formula. Well, in this case, you don't have that, but you need to remember that this number represents an x input. So, since 5 is the x input that's used in this symbol, I need to go to x equals 1, 2, 3, 4, 5 right here. And then, wherever the graph is at that point, that represents the y value that will be paired with an x value of 5. So, if there is a formula for this function out there, according to this being a point on the graph, if I plug 5 in as x input, it should give me 2 back as y output. And that's what you're prompted for there. What is the actual output that will be generated by plugging in an input of 5? And the graph tells you that. Remember, a function doesn't always have to be represented by a formula. You can represent them by graphs as well. And the graph tells you everything you need to know. And one last review of increasing and decreasing intervals. Remember, detailing these intervals requires you to read the graph from left to right. So, as you begin the domain at -5, going from left to right, that first portion of the graph is decreasing until you reach the x value -2. So the first x-axis interval that gives me decreasing behavior is from -5 to -2. So I'll detail that here. Then once we pass the x value -2, this graph is on the increase until we reach this point, which is at x equals +2. So the next x-axis interval that gives us increasing behavior is between x equals -2 and x equals +2. Again, I'm using open parentheses or the interval notation here. And then once I pass x equals 2, once I pass that maximum, the graph is going downward. So that arrow indicates that it continues with that behavior for the rest of the domain of the function. So once you pass x equals 2, the graph continues to decrease from 2 all the way to infinity. So that's another decreasing interval, so that means I will union that with this.